Hi, welcome to another snow lecture, or ice lecture. I'm not sure what we'll get. Uh, since I didn't, I sort of rushed through the end of maximum modulus principle, and I guess a bunch of people were missing. Although we did have a regular class on Monday. Let me just go through it again. So we're gonna prove maximum modulus principle. Right. Okay. So this is a very useful consequence of Cauchy's integral formula, and it has so many different applications, and it basically says that if you have a holomorphic function and you look at its modulus, right? I mean, normally you cannot compare complex numbers, right? So if you want to compare something, say something has a maximum or something, well, you need to look at maybe the real or imaginary part, or maybe the modulus. So here we're looking at the modulus, right? And this theorem says that if the modulus of f achieves a local maximum, just need a local maximum. It could be a global maximum, right? You could just take a smaller, small domain, right? Then it's constant, right? I mean, for this, if we want to say that it's constant, we need to assume that it's defined on a domain, so that it's defined on a connected set, right? Otherwise, it would be constant in the in the component, right, where it achieves a local maximum, right? So if you have a holomorphic function on a connected open set and the modulus achieves a local maximum, then it's constant. By the way, there is a similar sort of a minimum modulus principle, and it's an exercise, but there it's not quite the same, because it could achieve a local minimum if it has a 0, right? So if f is 0 somewhere, then it could be a minimum, but otherwise not. It can achieve, the modulus can achieve local minima, but they're all zeros. All right, but it's just an application of the maximum modulus principle. You can think about how to do that. All right, so what's the basic idea? The basic idea is that Cauchy's integral formula says that that f is the average of its values on a little circle around the point. Now, if we're averaging a bunch of numbers, the average cannot be bigger than the numbers themselves, right? That's the basic idea. And if it is ever, achieves a maximum, if you have an average of the numbers and the average has the largest, it's the maximum of the numbers, then all those numbers were actually equal, right? That's the basic idea. So how do we do this? Well, let's suppose that f achieves a local maximum at some point. And without loss of generality, we can assume that that point is 0. Right? Now, also without loss of generality, we could assume that f of 0 is not just the local maximum, but it's also a real number that's non-negative, right? And the way that we usually write that is this. I mean, a priori, that sort of makes no sense, right? We cannot compare complex numbers, right? But whenever we say that, we mean that f is real and non-negative, right? Now, why can we assume this? Well, otherwise we could just multiply by some unimodular constant to make f at 0 be positive, right, or non-negative. I mean, if it's 0, things are rather simple, right? If the local maximum is 0. All right. So now let me just use a, just so that I have a, a little bit less to write. So gamma sub r is just the circle of radius r around 0. And suppose that r is small enough so that, because it's a local maximum, right? 0 is local maximum, so that we have this inequality, right? That f of z, the modulus of f of z is less than or equal to the modulus of f at 0, which is just f at 0 because, right? Because we assumed that f at 0 was non-negative. And it's supposed to hold in this entire closed disk around 0 of radius r, right? So, all right. So now let's apply Cauchy's formula. So we have f at 0, that's just the modulus of f at 0, and Cauchy's formula says that f at 0 is this thing inside the absolute values, right? Now, let's just write down what that is, right? In terms of as a dt integral, right? And notice something. Notice that I'm gonna get a whole bunch of cancellations, right? This is gonna cancel out this I over here, and this RIT is gonna cancel out this, right? So I just have, basically, whatever's left out here. It's gonna be important in just a moment. But now let's take this and let's take the absolute value inside. We get an inequality, right? That's the triangle inequality for integrals. We get this inequality over here, right? So this guy is less than or equal to here, all right? Now, because we assume that f is a maximum and on the whole closed disk of radius r, everything was bounded by f at 0. Well, we can bound the inside from above by f at 0. Right, but now this doesn't depend on t. This is just f at 0, right? I'm averaging, right? I mean, this is the average of the moduli of f, and over here it's the average of a constant thing, right? And so we're saying that that's equal to f at 0. Now you look at that and you notice that f at 0, bunch of inequalities. F at 0, right? So that means that this inequality over here and this inequality over here must be actual equalities, right? All of these things are equal, right? Now, in addition, we have, because again it's a maximum, local maximum, that this is true for all t, right? That's true. Well, if we look at this inequality and we notice that this integral is equal to this integral, therefore, if we put those two together, we get that the integral of this, of this expression over here, right, is equal to 0. So if we have an integral of something that's equal to 0, that's not enough to say that it's 0. But if you have an integral of something non-negative, which is equal to 0, then whatever's inside has to be 0. And so we have that this is 0, and therefore we have that the modulus of f on this little circle is equal to just f at 0, right? So now let's apply Cauchy's formula again. I mean, it's maybe a little bit of a, let's turn back a little bit. Notice what we proved was that the modulus of f on this little circle is equal to f at 0. Now, we could do it for all r small enough, so we really have that the modulus of f is constant now, right? I mean, at least in a neighborhood, right? So yeah, that's not we need more. We need f to be constant, not just its modulus, right? But it's, I mean, there's various ways to prove that once you have that the modulus is constant, the function is constant. But let's keep going with this sort of same argument, right? So let's try to prove that actually f is constant, not just its modulus. All right, so we have so this guy, that's what we have over here. We said that was an inequality, right? And Cauchy's formula says this thing, right? So we have that the integral of the modulus of f over this little circle, right, is the integral of f, right? So I can again subtract them, and the integral is 0. Now, if it's 0, its real part is 0, right? And that's actually the thing that I'm going to be interested in. So I have that because this integral is 0, it's and I dropped the 1 over 2 pi. It's not once it's 0, right? Who cares? So this integral is 0, therefore its real part is 0. Now I can take the real part. The modulus is real, right? So therefore, I can, when I take the real part, I'm taking, it's the integral of the real part of the inside. And so the real part of the inside, I get the real part out here, right? So this integral over here is 0, right? Now, the modulus is always bigger than the real part, right? That's just sort of basic geometry, right? However, I'm wherever I'm at, the distance from the origin is always bigger than the x-coordinate, right? So that holds for all real numbers, for all complex numbers. Sorry, right? So therefore, this this guy over here is non-negative, right? That's the thing that we said the integral of that was 0, right? So we're using this argument again. The integral of a non-negative function is 0, therefore that non-negative function is actually 0, which means that we have that the modulus of f is equal to the real part of f, right? For points on this circle, right? For all points on this circle. Well, that means that if the real part is equal to the modulus, that means that the imaginary part has to be 0, right? The only way, right? The modulus, if the imaginary part was non-zero, then the modulus would be actually bigger, right? Because it's the square of the real part plus the square of the imaginary part, square root of all that, right? All right, so that means that the imaginary part of f on the circle has to be 0. Well, what does that mean? That means that the f, right, is real, therefore its real part is equal to f, right? So therefore we have that f is equal to modulo of f on the circle, which we proved was equal to f at 0, right? So this is for all t, meaning on the entire circle. And this held for all small enough r, right? For all small enough r, so that we could apply this, we were using that it was a maximum, local maximum, right? So where f was bigger than all the points in in an R neighborhood. Well, so once it's true for all small enough r, I can just, it's true for all little circles, then it's, f of z equals to 0 on a whole closed disk, right? Actually, on a whole open disk, right? I mean, that's the main thing. It's in a whole neighborhood of 0, right? F of z is equal to f of 0, right? It's constant in a neighborhood. Now, okay. So therefore, the identity theorem says, right? I mean, if I take f of z minus f of 0, right? that function would be 0 on an open subset or non-empty open subset. Therefore, the identity theorem says it's constant everywhere, right? So it's, f of z is equal to f of 0 for all z in U, right? All right, so that's the proof, right? So we have that, if we ever achieve a local max, we can do that, but then it's kind of for a stupid reason. The function is constant. Now, there's a corollary, and this is a sort of a useful corollary. It's suppose that I have, now a bounded open set, right? It should be non-empty for, just that's technicality, but it should be an open bounded set. The point is that once it's bounded, you're going to get that the closure is compact, right? So the closure of U is compact. And suppose that I have a continuous function on the closure of U. And suppose, so it's continuous on the closure, so including the boundary. And then if I restrict to the inside, I have a function on U, right? And we're assuming that that guy is holomorphic. That this version of the maximum principle says that that the modulus achieves. We know that it achieves a maximum somewhere on U bar on the closure of U because it's a compact set, continuous function on a compact set. All right, that achieves a maximum somewhere. So this says that it achieves a maximum on the boundary, right? So somewhere on the boundary, it must achieve the maximum, right? Maybe it achieves a maximum inside, but that really just means that it's constant inside. So we know that it achieves the maximum on the boundary, right? Now, in other words, another way of writing it is that if I take the supremum of f over the inside, which is the same thing because by continuity over the closure, but so if we take the supremum of f over the inside, it's bounded by the supremum of L, or the modulus of f, over the boundary, right? So that's the key points here are, here we're taking the supremum over just the inside, and here we're taking the supremum over the boundary, right? So maybe, just a little picture out here, right? So we have, we have our U, right? And the boundary of U is this red line, right? And we're saying that if we have a holomorphic function that's continuous on the closure of U, so continuous up to the boundary, then you have that you can just look on the values of f on the boundary, and if you can figure out a maximum for those, you have a maximum for f, right? It cannot sort of be bigger somewhere inside, right? At some point out here, right? That's not possible. So, all right. So that's the second version, and the proof of that is an exercise. It's not hard. All right. So that's maximum principle. So let's stop this.